This video will demonstrate how to perform the thin layer chromatography technique. Chromatography is a method used to separate different components in a mixture based on how fast or how slow they migrate with the liquid phase through a solid phase such as silica gel. Displayed on screen there are two definitions, absorption and adsorption. You are likely more familiar with the term absorption. Absorption refers to a solution actually permeating into a solid. The common example used to explain this is a sponge. Water will actually enter inside the sponge. Adsorption is a little less intuitive. The process of adsorption is when something adheres to the surface of a solid. To understand this process, think of the Velcro catch and throw paddles. When the tennis ball is thrown, it will stick to the Velcro paddle, but it will not go through. We have all seen before the do not eat packages in our clothes pockets and backpacks. The material inside of these packages is an adsorptive material and it keeps new products dry since the moisture will adsorb to the package's contents. These packets actually contain silica gel, which is the most common stationary phase in normal phase TLC. This brings us to a new set of definitions, mobile phase and stationary phase. These terms are pretty self-explanatory. A mobile phase will be a liquid which will move through the stationary phase which does not move. There are two types of chromatography, normal phase and reverse phase. In normal phase chromatography, the mobile phase is a non-polar solvent such as hexanes or ether, and the stationary phase is a polar solid. The most commonly used stationary phase is silica gel, which has a polar hydroxyl group on the surface of the silica. Reverse phase chromatography is the opposite to that, having a polar mobile phase and a non-polar stationary phase. Normal phase chromatography is the most common. Reverse phase chromatography uses a much more expensive stationary phase and therefore is not as practical in an undergraduate lab. In this experiment, you will be performing thin layer chromatography, commonly called TLC. Each different compound will move at its own characteristic rate through the silica gel, causing them to separate out into different spots on the TLC plate. TLC is used to determine the number of different compounds in a sample and identify the compounds in the sample. Compounds are then identified by comparing their migration rate to those of standard compounds which are run on the same plate. To perform TLC, you will need a 10 milliliter graduated cylinder, a TLC jar, a fluorescent or a non-fluorescent TLC plate, a capillary tube, tweezers, a pencil, the solution to make your mobile phase, and your sample. Your sample may be a liquid or a solid. The mobile phase for the first part of this experiment is 40% ethanol and diethyl ether. You may find both of these chemicals in the last fume hood, and you may only use them within the fume hood. The mobile phase solution can be prepared by measuring 4 milliliters of ethanol into a 10 milliliter grad cylinder and topping it up with diethyl ether to 10 milliliters. Add your solution to the TLC jar and quickly cap it. You want solvent vapor pressure within the TLC jar to be as high as possible for later development of your TLC plate. You may increase the vapor pressure by gently swirling the solvent inside of the jar. You can also take a filter paper and adhere it to the side of the jar with the solvents as shown here. This step is not necessary but may make the development stage faster. The stationary phase will be a thin layer of silica gel fused onto a plastic plate. This is your TLC plate and should always be handled by tweezers or gloves. There are two sides to the TLC plate, the smooth, clear-looking side and the rougher solid white side. The solid white side is the side with the silica gel, so that will be the side to which you will load your samples. The TLC plate is likely already going to be cut for you. The side with the corners cut off will be the bottom of the plate. If the corners are not cut off, then it does not matter which side is the bottom. It is very important to avoid any contact with water, which binds to the silica gel and deactivates it. There will be 2 plates available to you in this lab. For the first part, you will need the non-fluorescent plates, since you will be working with visible ink. For the second part, you will be working with clear liquids and you will need to use the fluorescent plate. If you do not use the fluorescent plate, you will not be able to see your sample and you will have to restart, which is not something you will want to have to do. Once you have chosen the proper TLC plate, to prepare your TLC plate, first draw a line 1 centimeter from the bottom of the plate. Whenever you are writing on the TLC plate, ensure you are using pencil and not pen. Pen uses ink, which will greatly interfere with your results. So, with my pencil, I am drawing a line 1.1 centimeters across the bottom. This line will be referred to as the origin. It does not have to be perfectly straight, so do not stress too much about that. Just make it as straight as you can. This is the line to which you will be putting spots of your samples. Count how many samples you are considering. Measure the width of the plate and determine an appropriate spacing. Remember, you must leave spacing between the edge of the plate and the sample spot, so take that into account as well. Generally, the spacing will be about 0.4 centimeters apart. Gently make a point after an appropriate spacing interval, and under each spot, label what you will be putting there. For the first part of the lab, you will be studying Sharpie colors, and you will also be considering what an overloaded sample looks like. I will write the colors next to each dot. Write each word slowly and softly as to not damage the silica gel. To spot the plate, take the marker and quickly and lightly dab it over its assigned spot. Do this with all of the markers. When you get to the overloaded spot, push a little bit harder and hold down for longer. Once all of the spots are finished, you can now run your sample. To do this, quickly open your TLC jar and gently drop in your TLC plate. Now all you have to do is wait and watch. You are looking at the motion of the solvent line up the plate. This is the motion of the mobile phase through the stationary phase. The solvent line will rise quickly at the beginning and more slowly towards the end. Wait until the solvent line reaches about 1 centimeter from the top of the plate. Once you see this, open the jar, remove the TLC plate with tweezers, and set it on the lab bench silica gel side up. It is important that you do remove the plate in time. If the solvent line reaches the top of the plate, you will have to restart. If the solvent reaches the top of the plate, the solvent will no longer be migrating, but the compounds will be. This will lead to erroneous results. Once you remove the TLC plate from the TLC jar, quickly trace the solvent line with pencil. Since the analysis considered Sharpies, the components are visible without UV light. Wait until the solvent dries and then circle the migration spots. You will be able to tell when the silica gel is dry, since you will be able to see the solvent evaporating. Be careful when you are doing this as to not damage the silica gel. It is very delicate. You should now laminate the plate with tape onto your report sheet. Once the tape is on, do not try to remove it or you will take off the silica gel. If you make a mistake while taping it, don't try to fix it. Just put more tape over it. The procedure for the second part, the identification portion of this lab, will be identical to the procedure for the colored ink portion, except you will need the additional skill of how to spot TLC plates with a liquid, and you will also have to use a different type of TLC plate. For the separation of different inks in part 1, all of the migration spots were visible since they were different colors of ink. Generally, you will be separating solutions which are only slightly colored or colorless, and therefore the migration spots will be invisible. How will you be able to determine the migration of a spot without being able to see the spot? To overcome this, fluorescent plates are used. Fluorescent plates have silica gel as their stationary phase, but with the addition of a fluorescent material. When the fluorescent material comes into contact with the components in the solution, the plate will fluoresce differently in those spots, and you will be able to visualize the migration spots. To actually use a solution to spot the TLC plate is the technique which will be applied in most labs. In order to accomplish this, take a capillary tube and immerse the tip into the liquid you will be studying. Make sure not too much liquid entered the tube. If you feel too much liquid entered the tube, touch the end of the tube to some paper towel or Kim wipe to allow some liquid to drain out. An appropriate amount of liquid is less than 1 millimeter. Once you have an amount close to 1 millimeter, touch the end of the capillary tube to the labeled spot on the plate. Do this quickly and gently. The dot should have a diameter no more than 1 millimeter. For this portion of the lab, you will be spotting 4 standard complexes and the unknown sample assigned to you. If your sample is solid, you will first have to dissolve it into an appropriate solvent. An appropriate solvent for this experiment will be ethanol. The standard samples will have flagged capillary tubes specifically for that compound as shown here. Ensure that you do not cross-contaminate samples by mixing up the capillary tubes. If you must use the same capillary tube for 2 samples, wash the capillary tube by dipping it into a bath of acetone and allowing it to dry by dabbing it on a Kim wipe. Once you have run your TLC plate as previously shown, you will not be able to see any spots. To visualize the spots, put the TLC plate under the UV lamp found in the balance room. UV light is dangerous, so do not look directly into the light. Under the UV light, you can now see the spots. Again, gently circle the migration spots. For the identification of your unknown sample, you can measure and compare the migration distance of each compound spot from the sample mixture to the migration distance of the standard spots. The migration distance of the sample spots cannot be matched to standards run on a different TLC plate. This is because the migration distance of a particular compound depends on the size of the TLC plate used and the speed the mobile phase travels. So the same compound will have very different migration distances on different TLC plates. In order to have a single characteristic migration value for a particular compound, we can calculate and report the retention factor. This is the ratio of the compound migration distance to the solvent front migration distance. This ratio is the same for the same compound on different TLC plates. To calculate the retention factor, measure the migration distance of the spot from the line at the bottom and the distance of the solvent line from the bottom. Shown here is an example of what you may see on your TLC plate. Retention factor is equal to the migration distance of the spot over the migration distance of the solvent line. This number will always be between 0, the spot did not move at all, and 1, the spot migrated the same distance as the solvent. Displayed here are the calculations for the retention factor for this TLC plate. To calculate each retention factor, I took how far the spot migrated and divided it by how far the solvent migrated. One compound may have more than one spot, like compound C. If that is the case, you must calculate the retention factor for each spot. Once you have done this for all of the spots, compare the retention factors of the unknowns to the retention factors of the standards in order to determine the identity of the unknowns.
Going back to our TLC, we can see that the unknown has the same RF value as the standard in the leftmost lane. Therefore, we can conclude it is the same compound.
The reason why the different compounds in a solution will migrate different distances is because of their different chemical structures, specifically their functional groups. As you know, different functional groups have different polarities. Some common functional groups and their relative polarities are shown here. In normal phase chromatography, the stationary phase is polar and the mobile phase is nonpolar. As compounds travel through the silica, they continually adsorb to the silica surfaces and desorb back into the mobile phase. Remember, like dissolves like, so polar compounds will adsorb more strongly to the polar stationary phase, whereas nonpolar compounds will only adsorb weakly to the silica. The more polar compounds spend more time adsorbed to the silica gel and will move more slowly compared to a less polar compound. More polar compounds will have lower RF values. Conversely, the more nonpolar a compound is, the less it is slowed down because it interacts less with the silica gel, resulting in a higher RF value. Ideally, you want to have a solution which will separate all the components in a solution. If you find that the mobile phase you chose led to two spots either not migrating at all or both migrating to the top of the solvent line, you may want to consider using a different mobile phase. Here, the eluent strengths of some common solvents. Here are the eluent strengths of some common solvents. Notice that the elution power is directly related to the polarity of the solvents. If none of your spots migrate at all, consider using a stronger eluent. If all migrate to the top of the solvent line, consider using a less powerful eluent. You may have to mix 2 or more solvents to get the desired polarity, as you will perform in this lab. From what you have learned about migration distance and polarity, which of these compounds is likely the most polar? Since compound B has the smallest RF value, the compound migrated the smallest distance and is likely the most polar. Compound C2 would be the least polar since it traveled the greatest distance. So to recap, first prepare your mobile phase by measuring 4 milliliters of ethanol into a 10 milliliter graduated cylinder and then fill to the 10 milliliter mark with diethyl ether. Pour the solution into a TLC jar and close the lid. Take your fluorescent or non-fluorescent TLC plate and draw a line 1.1 centimeters from the bottom. Make equally spaced dots along the line and label the dots according to what spot you will be putting there. To spot the TLC plate with a Sharpie, quickly dab the marker on the desired spot. To spot the TLC plate with a solution, take the capillary tube and submerge it into the liquid. Use a Kim wipe to drain out excess liquid, and then quickly and gently touch the end of the capillary tube onto the TLC plate in the desired spot. Place the TLC plate into the TLC jar and close the lid. Allow the solvent line to reach about 1 centimeter to the end of the plate. Remove the TLC plate, trace your solvent line. Either circle the visible spots once the solvent has dried, or take to the UV lamp to visualize the spots and then circle them. It is important that you do remove the plate in time. If the solvent line reaches the top of the plate, you will have to restart. If the solvent reaches the top of the plate, the solvent will no longer be migrating, but the compounds will be. This will lead to erroneous results.
There may be a situation where your unknown spot may have an RF value which is similar to a standard spot, but not identical. When this is the case, you may run a TLC plate and spot the unknown and the standard on the same spot. Once the TLC has been developed, if there are 2 spots, then the unknown is not the standard. If there is only 1 spot, then you likely accurately classified your standard.